This episode of Cosmos will take you to the celestial body that orbits closest to the Sun, the planet Mercury. Delve deep into the mysteries surrounding its genesis and explore its distinct physical characteristics. Learn about the bizarre outcome arising from the resonance of Mercury's axial rotation and orbital motion. Grasp the intricacies of the planet's unusual internal structure and discover its chemical composition. Examine the surface gravity, weak magnetic field, and almost non-existing atmosphere. Bear witness to the awe-inspiring landscapes of Mercury and enjoy the beautiful panorama from orbital perspective. Retrace the footsteps of the pioneering space missions in their investigation of the smallest planet in the solar system. Sit back, relax, and enjoy the show. Mercury. The closest planet to the Sun and the smallest one in the solar system. Its earliest documented observations trace back to ancient Mesopotamia, dating from the 1st millennium BC. Mercury is only visible to the naked eye when it appears near the horizon during twilight, just before sunrise or after sunset. This pattern led ancient Greek astronomers to mistakenly perceive it as two different objects. In modern times, the planet's name comes from ancient Roman mythology, where Mercury, analogous to the Greek god Hermes, was a messenger of the gods and guardian of all travelers. Mercury is nearly 3 times smaller than Earth and is the second densest planet after our own. By comparison, it is about 40% larger than our Moon. While Jupiter's moon Ganymede and Saturn's moon Titan surpass Mercury in size, its higher density renders it more massive than both. Mercury claims the title of the fastest-moving planet in the solar system and has a highly elliptical orbit. At its closest point, Mercury is 47 million kilometers away from the Sun, and at farthest, it reaches 70 million kilometers. During its closest approach to Earth, Mercury spends more time in proximity to our planet than Venus. Its orbit has an inclination of 7 degrees to the ecliptic. The ecliptic is the plane in which the Earth orbits around the Sun. The orbital period of Mercury is equal to approximately 88 Earth days. At the same time, it rotates around its axis very slowly, with one full rotation taking almost 59 Earth days. For every 3 rotations around its axis, Mercury completes 2 revolutions around the Sun. Therefore, its axial rotation is in a 3-to-2 resonance to its orbital motion. That leads to an unusually long day, which lasts approximately 176 Earth days, or 2 entire Mercury years. An interesting phenomenon occurs on the planet during its closest approach to the Sun. At that point, called perihelion, every planet has the highest orbital velocity. During perihelion, Mercury's orbital velocity exceeds its axial rotation. To a surface observer, for a few days the Sun appears to slow its motion until it stays in a fixed position in the sky and then starts to move backward. Once the planet exits perihelion and reduces its orbital speed, the Sun resumes its normal east-to-west movement. Thus, on certain meridians, sunrise, sunset, and a second sunrise can be observed in succession. The axial tilt of Mercury is the smallest among all the planets and is only 2 degrees. This results in relatively uniform heating of its surface by the Sun. Yet, its highly elliptical orbit has a significant impact on temperature differences over the course of a year. At perihelion, the temperature of the illuminated part of the planet can be up to 150 degrees higher than at the farthest point in its orbit, known as aphelion. Even more noticeable are the temperature variations within a day. During the day, the temperature reaches over 430 degrees Celsius, and at night decreases to -180 degrees Celsius. Only in the polar regions of Mercury the temperatures are relatively constant, at around -90 degrees Celsius. That is due to the steep angle at which the sun's rays reach the poles, and the absence of an atmosphere that would facilitate temperature exchange between different parts of the planet. Mercury has no atmosphere because it is not massive enough, and its surface gravity is just over 1/3 that on Earth. The proximity of its orbit to the Sun prevents the retention of a gaseous layer, as heated atoms separate into space within a few hours. Mercury has only a highly rarefied exosphere composed of hydrogen, helium, oxygen, and sodium. Water ions have also been detected in the exosphere, although liquid water cannot exist on the surface. They originate from deep craters near the planet's poles, containing reserves of water ice. Even with slight heating, in the absence of atmospheric pressure, that ice transitions directly from a solid to a gaseous state. Mercury has a very weak magnetic field, equivalent in strength to about 1% of Earth's. It is presumed to form similarly to Earth's magnetic field, generated by the movement of liquid metal within the planet's core. The tidal effect of the Sun maintains a sufficiently high internal temperature to sustain this process. Despite its weak magnetic field, Mercury does have a magnetosphere, which captures some of the high-energy particles coming from the Sun. However, the magnetosphere is unstable and can't shield the surface from the impact of the solar wind. At first glance, the surface of Mercury appears quite similar to that of the Moon. We can distinguish craters, plains, and seas of solidified magma, which indicates that the planet has not been geologically active for billions of years. Most craters were formed about 4 billion years ago, during the late heavy bombardment with asteroids and comets. Their sizes range from a few centimeters to hundreds of kilometers in diameter. If you are enjoying this video, give it a thumbs up and share it with your friends. Subscribe to the channel and hit the bell button to be notified of new episodes. You're welcome to post questions, thoughts, and recommendations in the comments section below. If you value our work and like to support it, please consider donating and visit our Patreon page. Join us on social media to stay updated with the latest space news and short clips on upcoming topics. Keep watching Cosmos to learn more. The largest crater, named Caloris, has a diameter of approximately 1,500 kilometers. The object that formed it was about 100 kilometers in size. Its impact was so powerful that mountain ridges up to 2 kilometers in height formed around the crater's periphery. Around it, similarly to other craters, bright radial rays of ejected material are clearly visible. On the opposite side of the planet, the terrain has chaotic relief and a relatively small number of craters. This topography is presumed to have originated as a result of the encounter of shock waves generated by the collision at Caloris crater. The plateaus between the craters are uplands with an uneven surface and are part of the planet's oldest crust. Yet, more common are the low plains resembling the lunar mares. They have formed due to volcanic activity following the late heavy bombardment, thus having fewer craters. Also noticeable on Mercury's surface are ridges up to 3 kilometers high, stretching hundreds of kilometers. Their formation is owing to the contraction of the inner layers caused by the planet's cooling. That has led to the subsidence of its already solid crust. The contraction process has reduced the planet's radius between 4 and 7 kilometers. Mercury's shape is close to a sphere, slightly bulging at the equator. The difference between its equatorial and polar radius is less than 2 kilometers. The equatorial radius has an average length of 2,440 kilometers. The planet is mainly composed of metals. They account for about 70% of its mass, and the remaining 30% are silicate rocks. The structure of Mercury consists of 4 layers: crust, mantle, outer core, and inner core. The crust has an average thickness of 25 to 35 kilometers. It is made of hard rocks containing magnesium, silicon, sulfur, aluminum, calcium, and potassium. Beneath it lies the mantle, approximately 400 kilometers thick. Chemically similar to the crust, the mantle is partially molten, with higher sulfur content. Beyond the mantle begins the outer core, surrounded by a solid layer of iron sulfide that acts as a thermal insulator. The outer core contains iron and nickel, with possible traces of sulfur, carbon, and silicon. The lower melting temperature of these elements has likely enabled the outer core to remain in a liquid state. The inner core is solid and contains mostly iron. It has a diameter of about 2,000 kilometers, comprising half the size of the entire core. Mercury has an uncommonly large core, accounting for almost 85% of its total volume. That raises questions about its formation process. Several hypotheses have been proposed, most of which refer to the planet's proximity to our star. According to one of them, much of the lighter elements in the protoplanetary disk near the Sun were removed from the orbit in which Mercury formed. That occurred due to friction and the gravitational attraction of our star. Mostly heavy elements like iron remained, forming a massive planetary core, but relatively few silicates, from which the thinner crust and mantle were shaped. Another hypothesis suggests that the high content of heavy elements can be explained by the Sun's magnetic field, whose strength decreases with distance. A large amount of metallic particles was attracted in orbits closer to the star, while in more distant ones, their concentration diminished. This claim is supported by the percentage of iron found in the cores of Venus, Earth, and Mars, which progressively decreases with distance. Observations of other planetary systems also point to a similar correlation. Some researchers propose that Mercury was formed during the earliest stages of the solar system and was twice its current size. The young Sun was much hotter then, and its heat vaporized the planet's outer layers, then carried away by the solar wind. This hypothesis is subject to strong criticism since relatively high concentrations of potassium and sulfur have been detected on Mercury's surface. These elements easily evaporate at very high temperatures and should not be present nowadays. The most impressive point of view is that Mercury was formed further away from its current position and was at least twice as massive. As a young planet, it resembled the early Earth and Venus. But a collision with another protoplanetary body broke off much of its crust and mantle and sent the planet into a closer orbit around the Sun. This assumption may also explain Mercury's tilted and highly elliptical orbit. Alas, such an impact would have vaporized much of the lighter elements, and they should not have their present concentrations on its surface. The existence of many hypotheses about the origin of Mercury is a testimony to our limited knowledge. The proximity to the Sun makes it one of the most challenging objects to observe with a telescope. Mercury is also one of the least studied planets in our system. Sending probes into orbit also poses a significant challenge, on one hand, due to its high orbital velocity, and on the other, the powerful gravitational field of the Sun. A spacecraft launched from Earth would have to carry too much fuel to be able to reduce its speed sufficiently. Otherwise, it would not be able to stay in orbit and would be pulled in by our star. In other words, it's easier to send a probe to the periphery of the solar system than to Mercury. For this reason, there are currently only 2 spacecraft that have reached this planet. The first one is NASA's Mariner 10, sent in 1973. In order to achieve the necessary velocity, it used a gravity assist by Venus and positioned itself in orbit closer to the Sun. Mariner 10 flew by Mercury twice in 1974 and again in 1975 before depleting its fuel. During its 3 flybys, Mariner 10 photographed about 45% of the surface and detected the presence of a weak magnetic field. The next mission to Mercury was also by NASA and was called Messenger. The probe was launched in 2004 with the goal of entering an elliptical orbit around the planet, using 1 flyby of Earth and 2 of Venus. In 2008 to 2009, it passed by Mercury 3 times, and in 2011 entered orbit. It managed to capture the entire surface and sent nearly 100,000 high-resolution images. Messenger was equipped with instruments designed to study the chemical composition of the crust and exosphere, magnetic field characteristics, and the planet's internal structure. The project was successfully completed in 2015, after which the spacecraft fell to the surface. A third mission to Mercury is also on its way, launched in 2018. It is called Bepi Colombo, named after the Italian engineer Giuseppe Colombo, who first proposed the use of gravity assist to reach the innermost planet. The project is a joint venture between the European and Japanese space agencies, expected to enter orbit around Mercury by the end of 2025. The spacecraft consists of 2 separate modules. One will focus on studying the planet's magnetosphere, while the other will conduct numerous detailed measurements of the planet's physical and chemical characteristics. The orbital mission of the probes will extend over a period of 1 or 2 years, shedding light on many unanswered questions. Future exploration of Mercury will contribute to a better understanding of the processes that led to the formation of the solar system and all terrestrial planets, including our own. Therefore, the relentless quest for knowledge drives humanity to conquer the most inaccessible places of the nearby cosmos.